So what happens with polyprotic acid? So a polyprotic acid is one that has more than one proton, so at least two protons that it can donate. And I mentioned this earlier. So remember that they won't donate them all at once. They're going to do it in two steps. And so we can set up an acid equation for each of the different ions. All right, so sulfuric acid, for example, can lose two protons. The first acid equilibrium expression is H2SO4 plus H2O gives us H3O plus HSO4 negative. And notice the Ka value for that, 1.7 times 10 to the minus 2. So it's actually pretty large, and we generally say that sulfuric acid completely dissociates. Anyway, once that HSO4 negative is in solution, it can actually also react with water as an acid. And so this is our second dissociation equilibrium. HSO4 negative plus H2O gives us H3O plus SO4 negative 2. And notice that that expression also has a Ka value related to it, 6.4 times 10 to the minus 8th. And as we discussed before, the second equilibrium is the second acid, the second proton, the second H plus is much less acidic than the first, and so the Ka value is much smaller. So in some cases, like the H2SO4, we often don't have to consider the second equilibrium because the H plus from the first one is so large. But actually, it depends on what you're looking for, whether you need to worry about the second equilibrium equation or not. So here we're going to just look at an example, like carbonic acid is just another example, and we have to consider both of the reactions, both the H plus, the first H plus that's given up, and the second. Okay, so here we have our first equilibrium, H2CO3 gives up one H plus to give us H3O plus HCO3 negative. And then the second HCO3 can also react to give H2O a proton to become H3O plus and CO3 negative 2. So we're going to look at what's going to happen if we have to consider both equations. All right, so we do know that each equilibrium has a Ka value associated with it, and we can write the Ka expression. So for the first reaction, we have a Ka of 4.3 times 10 to the minus 7th, and you can see here we have H3O plus times HCO3 negative over H2CO3. Then for the second proton, we have another Ka expression. This time it's CO3 negative 2 times H3O plus over HCO3 negative. And you can see there's a second Ka value, 4.8 times 10 to the minus 11th. And again, we know that the second Ka is smaller than the first Ka. What I just said, in general, the second ionization constant will be smaller than the first ionization constant. If there's three of them, then there will be three Ka values. And for H3PO4, we noted earlier that the first Ka is the largest, the second Ka is smaller, and then the third Ka is even smaller. It could be fairly complicated to do some equilibrium compositions. And it sort of depends on the difference in the Ka values between the two acids, the two different steps, and also what the initial concentration is, and also what you're looking for. I think we're going to do an example in just a minute. We're going to make some assumptions and make some simplifying assumptions like we've done in previous problems, and make even more possibly to see what happens with the second equilibrium. All right, so let's look at this example. Ascorbic acid, vitamin C, is a diprotic acid, H2C6H6O6. The question is, what is the pH of a 0.1 molar solution? And then the second question is, what is the concentration of the ascorbate ion, C6H6O6 negative 2? So we kind of need to know what is the concentration of that after both H pluses have been lost. So we're going to consider each of those questions. We're given the acid constants, Ka1, 7.9 times 10 to the minus fifth, and Ka2, 1.6 times 10 to the minus 12th. All right, so what we want to do first is figure out the original first step. It'll turn out, and we'll see that the H plus ion concentration is going to be so much smaller because the Ka2 is so much smaller than the Ka1. So we'll see when we get the answer, we'll see what we can do, and we can see that it can be neglected. But for right now, we're just going to kind of go through both steps of the problem and see what happens. We do have to go through the second step because they're asking us what is the concentration of the ascorbate ion, which is only evolved from the second step. All right, so let's look at the first step, and they're abbreviating ascorbic acid as H2ASC just to make things simpler. I'm not sure why, but that's okay. So notice that the first step, 1 H plus is transferred to H2O. So we have H3O plus and H ascorbic ASC negative. So we already know how to write the equilibrium expression, and we have the Ka value 7.9 times 10 to the minus fifth. And now we can write our ice chart. So we know our initial concentration of ascorbic acid is 0.1. H plus and H ascorbic are 0 until equilibrium is established, and our equilibrium values then are 0.1 minus X, what we started with, minus the amount that dissociates. Our H3O plus is equal to X, and our H ascorbate is also X. So if we plug it into our equilibrium expression, we get x squared over 0.1 minus x equals 7.9 times 10 to the minus fifth. We're going to be able to do our simplifying calculation to see if we can ignore the minus x in the denominator. So here we do that. Ca, 0.1 divided by Ka, 7.9 times 10 to the minus fifth is over 100. So we can make that simplifying assumption. So we say x is much smaller than 0.1, and we have x squared equals 7.9 times 10 to the minus fifth, and then multiply by 0.1. That was in the denominator. So x is 2.8 times 10 to the minus 3, or in other words, 0.0028. And in fact, that is much smaller than 0.1, at least to any significant figure calculation. All right. So the H plus concentration is 0.0028 molar, and pH is 2.55. All right, so we are at this point ignoring the H plus from our second equilibrium. When we do the calculation, we'll see that in fact it can be ignored because the Ka2 is so much smaller than the Ka1. But for right now, we'll go with this. We'll say the H3O plus is 0.0028, and so our pH is 2.55. So now we want to concentrate on the second question. What is the concentration of the ascorbate ion, C6H6O6? For that, we're going to have to use our second equilibrium expression. Now, I'm going to call the ascorbate ion Y, just to make it simpler and to keep it different from the previous equation where we used X. You can call it whatever you want to. You can call it X2 if you want to, where we did X1 in the first equation. But I'm just going to call it Y, just so that we know it's different from the first equilibrium expression. All right, so here's our second step. HASC negative plus H2O gives us H3O plus the ascorbate ion, ASC negative 2. And again, we have our equilibrium expression that we know, products over reactants, and we know the Ka, 1.6 times 10 to the minus 12. So let's set up the ice. So there's our ice chart. Now, I do want you to notice one thing. The initial concentration of the HASC we got from the first part of the problem is 0.0028. Remember, that was X, and that was actually a product from our first reaction. We also know that the H3O plus concentration is also 0.0028 after that first step, because remember, both of those were on the product side and they were each equal to X, which was 0.0028. So this is the first time that we see something on the right hand side, because H plus is always already around from the first step. So notice that that's 0.0028. But the ascorbate has not appeared yet, and so it's still 0. Now we're going to call this equilibrium, like I said, Y, just to make it different from the last one. So the 0.0028 of the HASC, and it's not the same as the original 0.1 because only a small percentage of the H2ASC has broken apart. So for the second step, we're only starting with what has how much of the HASC negative has appeared, which is 0.0028. All right, so we're going to subtract Y. And on the other side, the amount of H3O plus, the additional, we'll have to say the additional amount is Y, and then the ASC negative 2 will also be Y. So now we have our equilibrium expressions, 0.0028 minus X, 0.0028 plus X for the H3O plus, and we'll see in a minute how this will or won't change the pH. And then the ascorbate is also Y. So now we plug this into our equation. Here's our equilibrium expression. Plug the numbers in. Okay, and we have 0.0028 plus Y times Y over 0.0028 minus Y equals 1.6 times 10 to the minus 12. Now we can still do our simplified, that looks like a really complicated equation to solve, but luckily we can do our simplifying expression again. This time our CA is 0.0028 and our KA is 1.6 times 10 to the minus 12. So let's see what that gives us. CA over KA gives us 1.8 times 10 to the 9th. So that is quite a bit bigger than 100. So in fact, X is going to be much, much smaller than 0.002H, which is sort of what we predicted from the beginning, but we'll go with it. So since X is so much smaller than 0.0028, we can ignore it when subtracting it. We can also ignore it when adding it. So both the Y gets omitted from the plus on the top and from the minus Y on the bottom. So you can see 0.0028 times Y divided by 0.0028. That's a pretty easy expression to solve, where that cancel out, and we see that Y equals 1.6. So we can see that Y equals our ascorbate ion concentration, which is 1.6 times 10 to the minus 12, which is very, very small. Also, just note, to go back, remember we said that we figured out the pH only from the first equilibrium expression. We took the H plus concentration to be 0.0028 and found the pH from that. Technically, the H plus concentration is 0.0028 plus Y, which we found out to be 1.6 times 10 to the minus 12. But clearly, 1.6 times 10 to the minus 12 is so much smaller than 0.0028 that it's not going to make a difference into our pH. So if you're just trying to find the pH of a polyprotic acid, you only need to consider the first ionization equilibrium. Now, if you are looking for the final ion after the second equation, you're going to have to go through the two-step process where you do it the first one and then plug those numbers in for the second one like we just did. But for the most part, if you're just looking for pH, you only need to worry about the first equilibrium expression. And in fact, you can ignore the second one. All right, so let's move on to base ionization equilibrium, which is going to be very, very similar to acid equilibrium. Basically what happens, you put a base in water. So here's ammonia plus water, and we saw this back in the last chapter. This time a base will accept a proton to become NH4 plus, and OH negative is produced. So, but the same thing is we set up an equilibrium. So we can rewrite our equilibrium expression. Kc equals products over reactants. Now we know again, like we saw before, that H2O plus is really a constant. So if we bring that over on the left-hand side of this equation, we end up with H2O times Kc equals NH4 plus times OH negative over NH3. And we're going to, since it's a constant times a constant, we're going to give it a new name, and we're going to call it Kb, which stands for the equilibrium base constant, the equilibrium constant for a base. So Kb. So here's our general equilibrium for a generic base. So if we just call the base B plus H2O, we know that the base is going to accept an H. So just for consistency's sake, we usually put the H on the front. You know, if it's an acid, we take it from the front. If it's a base, we put it on the front. So it becomes HB plus. Don't forget the H plus has added, and OH negative. And then our Kb will equal HB plus times OH negative over B. And so just like the acids, we can look up Kb values, and we can solve equilibrium, and we can also find the pH of a solution. There's just one little extra thing, is that notice that when we don't have H plus anywhere in our equation, we have OH negative. So we're just going to have to take one little extra step to figure out the H plus once we know the OH negative. But let's do an example. Okay, so first let's look at the expression. So again, if you're doing a problem and they don't give you the Kb value and you think you need it, probably it's here on this chart. So ammonia, 1.8 times 10 to the minus 5, some other common bases, aniline, urea, etc. So if you're working on a problem, the Kb might be found here. All right, so what is the pH of a 0.2 molar solution of pyridine, C5H5N, in an aqueous solution? The Kb for pyridine is 1.4 times 10 to the minus 9th. All right, so again, just like your acid, the very first thing you want to do, you want to set up your equilibrium expression. Write the equation, write the equilibrium equation. Then you're going to set up your ice table, your ice chart. We're going to set up our equilibrium constant expression, products over reactants equal Kb, and then you're going to solve for X. But just keep in mind again that X will now equal OH negative. All right, so here's our equilibrium expression. So C5H5N plus H2O, again, the base picks up an H plus. It doesn't really matter where you put the H, but just to make things consistent, put it in the front. So H, C5H5N plus OH negative. And then we set up our ice chart. So we know the initial concentration is 0.2. And then we're going to, some of it's going to accept a certain amount, will dissociate, or in this case, we'll accept an H plus, and we'll call that amount X. So 0.2 minus X at equilibrium, and then our conjugate acid will be X, and our OH negative will be X. Now we can plug that, we can do the same simplifying expression. This time it'll be Cb over Kb rather than Ca over Ka. So our initial concentration is 0.2, and our Kb, 1.4 times 10 to the minus 9th, gives us a value 1.4 times 10 to the 8th, which is much, much greater than 100. So in fact, when we have that minus X, we can ignore it. So 0.2 minus X will be about the same as 0.2. Again, we can't ignore it when we plug it in by itself, but when it's subtracted from a much bigger number, we can ignore it. So here's our equilibrium expression, and then we plug in our value. So X squared over 0.2 minus X equals 1.4 times 10 to the minus 9th. Now we're going to apply our simplifying equation, and we're going to say X is much smaller than 0.2, so we can ignore it. And so now we can just solve for X, multiply both sides by 0.2, and take the square root, and we get 1.7 times 10 to the minus 5. So just don't forget that at this point, X is 1.7 times 10 to the minus 5, which is our OH negative concentration. So to find the pH, you're just going to have to do one extra step. First thing we can do is find pOH. Negative log of 1.7 times 10 to the minus 5 gives us 4.8, but then we just have to subtract it from 14 to get our pH of 9.2. Since this is a base, it should have a basic pH above 7. 9.2. So it's really exactly the same thing, except that we're producing OH negative. We have a Kb just like a Ka. You write the expression, you write the Kb expression, and you solve for X.